Today, the oceans are full of swimming organisms, some streamlined and adapted to fast swimming. For a lot of these creatures, hydrodynamic efficiency, in other words, the ability to swim fast, is vital.
Well, it's easy enough to observe the swimming behavior of living sea creatures such as the shark in here. And so if you find some fossil shark's teeth in a sedimentary formation, you wouldn't have any trouble inferring the life habits of the kind of animal they came from. But what about a fossil sea creature such as this ammonite, which you wouldn't find alive today? How can we reconstruct its life habits? Well, we know that ammonites lived in the sea because we only find their fossils in marine sedimentary formations. Let's go further than that. Was it capable of swimming or not? And if it was, how fast could it swim? How is it possible to answer such questions about an animal such as this, which has been dead for over 100 million years?
Ammonites first appeared in the Triassic over 200 million years ago. Many different shapes and sizes of ammonites evolved in the oceans of the Jurassic and Cretaceous, and a wide variety of coiled external shells have been preserved in the fossil record. Despite this success, their numbers sharply declined at the end of the Cretaceous, and they had become completely extinct by about 65 million years ago. If we want to find out any more about the way ammonites live, we need to find a comparable living organism, and just such an organism is kept at the New York Aquarium by John Chamberlain.
One of the animals in the modern ocean most like ammonites is this one, Nautilus. Like ammonites, it's a cephalopod. It's rather like a squid whose body has been tucked into a hard shell. You can see, even though the body is retracted here, the large prominent eye, tips of the retracted tentacles, and the protective hood. Now, if you cut one of these shells in half, you get something like this, which is a shell cutaway showing the large chamber at the bottom of the shell in which the body is located, and a number of smaller chambers at the top, which in life are filled largely with air. This distribution of mass, of buoyant air chambers above and deadweight tissue below, imparts a high degree of static stability so that the animal can maintain a vertical orientation in the water to which it always will return if it's disturbed.
We know from the fossil record that Nautilus and ammonites had a common ancestry in the distant past. And because of this, we assume that the chambered shell of ammonites also acted as a buoyancy tank. This inference about the ammonites is based on homology, that is, that similarities in body form are thought to have had the same function because of their common ancestry. Both shells have a center of buoyancy located directly above their center of mass when they're in their normal floating positions. The ammonites were capable of stable floating, just like Nautilus. But of course, Nautilus doesn't just float around, it can swim too. All modern cephalopods, including Nautilus, can swim by jet propulsion, and it's most likely that ammonites swam along in the same way. Here, the motion has been slowed down 10 times. The large mantle cavity on the underside of the body expands and fills up with water around its lower rim. The head of the animal then contracts back into the body chamber and pumps the water out with surprising force through a funnel. But for Nautilus, and probably for the majority of ammonites, this rather inefficient locomotion doesn't matter too much, as it spends most of its life browsing over the sea floor. In the case of Nautilus, it can live as much as 200 meters below the surface. Another shortcoming of this arrangement is that they have to hump around this great big shell, as did the ammonites, which means that their power-to-weight ratio is very poor, especially compared with fish. And of course, the broad, blunt profile of such shells is hydrodynamically inefficient. It creates a lot of drag. Unfortunately, the thrust from this jet propulsion isn't in line with the center of buoyancy, and so some of the energy is transposed into a rocking motion which becomes more exaggerated the faster it tries to swim. Of course, this places a limit on its maximum speed. If it pumped too hard, it would start to turn cartwheels. One of the best examples of a streamlined hydrodynamic shape is the torpedo. It's designed to travel long distances at high speed by creating as little drag as possible. Any swimming animal encounters drag, but they're all adapted to counter it according to the needs of their lifestyle. Sharks, in particular, have evolved into efficient hydrodynamic shapes. Most of their body weight consists of swimming muscles, and this enables them to swim fast and hunt for prey and to conserve their limited supply of energy. Drag is the resistance generated by any object as it moves through a fluid. In the interests of better performance and lower fuel consumption, cars have evolved to more efficient shapes where the drag is reduced to a minimum, mainly by reducing the air turbulence behind the car. The problem of drag has been partly solved by another relative of the ammonites, the squid. They've overcome the problem by internalizing the shell. As a result, the center of buoyancy and the center of mass are coincident, and the jet propulsion thrusts the entire animal forward in a straight line. Although it no longer has the static stability of Nautilus, it can stabilize itself with fins that have evolved from the mantle, which has overgrown the outer surface of the shell. The squid has dynamic stability. The masters of this advantageous combination of hydrodynamic efficiency and dynamic stability are certain types of bony fish. Even though they possess swim bladders for buoyancy, their centers of buoyancy and mass are nearly coincident. The forward thrust, developed by the propulsive muscles, is directed along the midline of the body, very close to the center of buoyancy. Although many fish have a low static stability, their external fins can stabilize and change the attitude of their bodies dynamically. Of course, it's not only fish and squid which have come up with this solution for more efficient swimming. Other unrelated organisms have similar structures and functions. Quite a large number of mammals, like seals, have evolved into very efficient swimmers. Porpoises are also torpedo-shaped and produce very little drag. And even the shape of one or two birds is adapted so that any thrust is along the midline of the body. And this kind of adaptation isn't just a recent phenomenon. From the fossil record, we know that some reptiles lived in the sea and had also evolved highly streamlined shapes.
This is the mounted fossil skeleton of a marine reptile called an ichthyosaur. It lived about 150 million years ago. Now, from a number of its fossils, we can build up a pretty accurate idea of what its shape would have been like in life. Here's a scaled-down model of its rather porpoise-like body. Instead of arms and legs, it's got narrow, hydrofoil-shaped side fins, as well as dorsal fins and a tail fin. So we can infer by analogy with living efficient swimmers, such as porpoises and seals, that the ichthyosaur as well must have been an efficient swimmer.
But where does that leave our ammonites? Well, swimming, but rather inefficiently compared with the streamlined vertebrates and squids. In fact, only about 10 to 30% as efficiently. Their low power-to-weight ratio meant that they simply couldn't have been capable of sustained rapid swimming. Just how did this variety of shapes and sizes of ammonites match their lifestyles, and in particular, their swimming capabilities? On Long Island, in the laboratories of the Webb Institute of Naval Architecture, John Chamberlain has studied this problem by observing and measuring the drag on models of ammonite shells. Iodine crystals are glued around the front edge of the model. This is then placed in a steady laminar flow of water, which enables us to observe, by analogy, the flow patterns that would have existed around an ammonite shell, just as if it were swimming through the water. Water flows smoothly over the front of the shell, but then it stalls and separates from the shell in the central depression, which is called the umbilicus. And behind that, it breaks up into a turbulent wake. Most of the drag produced by these shells is directly related to the size of the umbilicus and the overall width of the shell. This one has a small umbilicus, so very little turbulence is created adjacent to the shell. It's rather the same with Nautilus. The flow lines are smooth over the sides of the shell, but swirl around into exaggerated vortices behind it. There are very few ammonites like this model, where the umbilicus is so large that the individual coils are separated. Turbulence is created behind each coil. It certainly wouldn't have been very good at fast swimming. Unlike these smooth-surfaced models, most fossil ammonites have ridges and ribs. These also affect drag. Rough surfaces generally increase drag. Experiments have been carried out on models of up to a few tens of centimeters in diameter, where the projection from the surface of these ribs is less than 1% of the width of the whole shell. In these cases, the drag can be reduced by as much as 35%. This dramatic increase in swimming efficiency was probably sufficient enough to make fine shell ornamentation an important adaptive factor in ammonite evolution. At first, this might seem a somewhat unexpected effect, but this method of roughening surfaces to reduce drag is fairly common. The size and the pattern of the dimples on a golf ball are instrumental to producing a low aerodynamic resistance. Because of the variety of ammonite shapes, it's convenient to describe their shell forms in terms of a number of simple geometric parameters. One of these, W, is the expansion rate of the shell as it coils around. In other words, the rate of increase in the size of the shell opening. In this computer-simulated growth, the aperture size only expands slowly on coiling. A high expansion rate produces a shell whose aperture expands more rapidly with coiling. Another parameter, D, shows the position of the aperture relative to the center of the shell. This affects the size of the central depression. These two shells have high D values. However, low D values produce shells where it's much more difficult to see the inner coils. The umbilicus is smaller. It's also important to realize that all these shapes can be flattened or compressed perpendicular to the coiling axis. Varying the parameters, W and D, can provide us with an array of all kinds of different shell shapes, representative of a variety of different ammonite shapes. The only way to quantify the hydrodynamic efficiency of each of these shapes is to measure their drag in a tow tank. This one at the Webb Institute is normally used for measuring the hydrodynamic performance of different hull designs. But it can also be used to measure the drag coefficients of specially prepared models of different ammonite shell forms. The model is supported under the water on a rod attached to a frame. The drag is translated via a spring to a calibrated scale. The first model we filmed had a reasonably low expansion rate, W, and a high D value. The drag measured was nearly 3. This model was then swapped for one with a high W and D value. When this was towed along the tank, it produced a drag measurement of almost 7, appreciably higher than the first shell. It's a very wide shape and is creating a great deal of turbulence behind it.
This graph of expansion rate and umbilical size helps us visualize ammonite shell geometry. Nautilus would plot about here. I found in my work that shells in this part of the graph have the lowest drag coefficients. And of these, 2 have particularly low drag coefficients, this one here and this one over here. Now, this one also has a high static stability, and most ammonites have morphology similar to this. Thus, it would seem that ammonite shell form is a compromise of low drag coefficient and high static stability. And now, compared to modern swimmers like fish, ammonites are much more poorly designed with respect to drag and propulsion. But the main diversity of well-designed fish did not occur until about the Cretaceous. Prior to the Cretaceous, and especially in the Paleozoic, ammonites were probably no more poorly designed than any other swimmers around them in the ocean at that time.
These shells belong to Placentisserus, the most hydrodynamically streamlined Cretaceous ammonite. Their relatively greater mobility and swimming speed allowed them to easily catch small open water prey, such as crabs and small fish, and greatly enhanced their ability to live in open oceanic environments. Their streamlining also allowed them to escape vertebrate predators through a series of rapid and erratic backward swimming motions, much in the manner of modern squids. Despite the presence of large vertebrate predators, marine reptiles and fish, in late Paleozoic through Middle Mesozoic time, the fossil record reveals no evidence that they preyed on ammonites. The ammonites indeed had a very good time of it, swimming unhindered through open seas in search of their prey without predation. Toward the end of the Mesozoic, in the late Cretaceous, however, things changed dramatically. By this time, a large reptilian predator had evolved with long stabbing teeth and powerful articulated crushing jaws capable of grasping and piercing ammonite shells. This ferocious beast is a mosasaur. It certainly looks capable of eating an ammonite, even a rapidly swimming type like Placentisserus. But how do we know that it did? Well, the evidence is here. Remarkably well-preserved mosasaur teeth marks in Cretaceous ammonites. Notice how the size and spacing of the tooth marks in the ammonite closely match the size and spacing of the teeth in the jaw of this mosasaur. This is Placentisserus, and it represents a form among Cretaceous ammonites that is most commonly predated by mosasaurs. By noting the way in which individual mosasaur bite marks modify one another on the ammonite shell, for example, the way that a tooth mark of the second bite intersects a tooth mark of the first, we can work out the order of biting, that is, the behavior pattern of the mosasaur. From the study of more than 30 predated ammonite specimens, a remarkably consistent pattern of mosasaur predation emerges, telling us how the animal dealt with this fast-moving prey. For example, if we position the ammonite this way, in life position with the eye approximately here, we can see that the initial mosasaur attack came from the blind side of the ammonite, that is, from below and behind. Even if the ammonite had sensed the presence of the mosasaur and had begun rapid escape motions, it would have swum backwards directly into the jaws of the predator. The initial bite of the mosasaur was designed to cripple and to destroy the flotation of the ammonite. For example, in this first bite, we see the jaw crossing the living chamber with the teeth penetrating and wounding the animal, and the empty chambers behind it, allowing gases to escape and destroying buoyancy control. The crippled ammonite was then positioned by the mosasaur in the jaw through a rapid series of gulping and chewing bites, further injuring the animal. Finally, the mosasaur let go of the crippled animal and homed in for the final time on the animal itself, grabbing the ammonite at the edge of the living chamber, crushing the thin shell in this area, grabbing the animal and ripping it from the shell with a rapid series of head shakes. The empty ammonite shell then settles slowly to the bottom. Toward the end of the Cretaceous, fossil evidence indicates that several types of mosasaurs had evolved predatory feeding habits on ammonites, mostly on these disc-shaped forms like Placentissaurus. Predated Cretaceous ammonites like these are rare, comprising less than 3% of all large specimens collected. This suggests that perhaps ammonites were only a secondary food source for the mosasaurs. But it also suggests to us that the hydrodynamically streamlined design of the ammonite shell, allowing for rapid, erratic backward escape motions when swimming, may have been a superb adaptation for survival in the open sea. Indeed, most ammonites may have escaped mosasaur predation.
Here we've been talking about one of the most streamlined ammonites, an open water swimmer whose adaptation for relatively rapid swimming may well have been associated with escape from predators. Most ammonites were not nearly so streamlined and must have been pretty sluggish swimmers. Many of these probably lived quite close to the sea floor. In this program, we've emphasized the different ways in which paleontologists can work out the swimming capabilities of extinct animals using homology and analogy with living organisms and with models. And we've also been able to use fossil ecological evidence like the mosasaur tooth marks.